Good afternoon, everyone. I'm Lingyun from HQST. Today, we are going to present Katz, an efficient workflow serving system for text-to-image diffusion models. This is a joint work with Alibaba Group. Text-to-image generation using diffusion models has become a popular service in today's AI cloud. It enables the creation of high-quality, contextual, accurate images from textual descriptions. It has matured as a service widely deployed in the cloud and data centers. According to the report of Adobe Firefly, it has generated more than 2 billion images by 2023. The existing text-to-image generation follows a diffusion process. It starts with an image composed of a random noise, and it progressively denoises this random input in iterations, until the output image aligns with the provided text prompt. This process normally happens in the latent space. The final latent tensor is sent to the Weiyi decoder to render the output image. However, only using textual prompts makes it hard to precisely specify layouts, styles in image generation. Even with the same prompt, the details of the generated images can be dramatically different. Therefore, the production text-to-image service is more than a base diffusion model. In the real-world applications, a base diffusion model is often augmented with adapters to better control the details of the output images, such as shapes, outlines, poses, and styles. Here, we illustrate the powerful effects of using ControlNet and LoRA. They are the two most popular adapters used in production. ControlNet here allow users to input a reference image to guide the spatial composition of the generated image. As illustrated in the figure, ControlNet enables users to provide a reference edge map, allowing the base model to generate a Ferrari that adheres to the specified spatial composition. LoRA is another popular adapter that allows for generating images in a customized style. The figure here shows a base diffusion model patched with a paper card LoRA can generate image in a specified style. ControlNets and LoRAs are prevalent in today's T2I services. We have collected a 20-day trace in a production platform, which includes 500,000 requests to text-to-image generation services. We can see that over 99% of the requests require at least one ControlNet, and over 90% of requests require at least one LoRA. In total, there are over 140 unique ControlNets and 14,000 unique LoRAs invoked in the trace. However, the use of the adapters poses new performance challenges. We compared the inference latency of requests using the existing system, Hugging Face diffusers, a state-of-the-practice system for diffusion model serving. As shown in the figure, the request inference latency increases as more adapters are in use. Considering the prevalent use of adapters, it is critical to address the challenges arise in serving them in a text-to-image workflow. In the rest of the talk, we will first uncover the challenges of different workflow serving with adapters and present cost designs. The first challenge is adapter loading. As the designed ControlNets and LoRAs are different across requests, they must be fetched from storage and loaded into GPU memory, introducing non-trivial loading overhead. In the trace, on average, each request needs to load at least one ControlNet and one LoRA, accounting for 37% of the end-to-end serving latency. Given the large population and size of these adapters, pre-caching all of them in GPU memory is infeasible. The second challenge is computation. First, ControlNet is compute intensive. ControlNet has a similar architecture to the base diffusion model. Adding one ControlNet to the serving workflow can extend the generation latency by 1.6 times. As more ControlNets are utilized, their computational overhead accumulates, leading to a significant latency increase. Besides, the base diffusion model itself is computationally intensive. As shown in the figure, across all three GPUs, doubling the batch size results in an approximately 2 times increase in serving latency. This indicates minimum benefits from serving multiple requests in the batch. Next, Suyi will introduce how Katz works out with 3 key designs, namely ControlNet-as-a-Service, bounded async LoRa loading, and optimized base model execution.
So first, Katz has a ControlNet-as-a-Service design. So according to the production trace, we found that there is a severe skewness in the access frequency of ControlNets. So the top 5 popular ControlNets can account for over 98% of the total usage. So therefore, caching a small number of popular ControlNets can eliminate the loading overhead, which is shown in our figure. And to reduce the computational overhead of ControlNet, Katz supports ControlNet parallelization, which concurrently executes ControlNet and the base model on multiple GPUs. And this is the diffusion model specific design, which is very different from the tensor parallel or the pipeline parallel. So with ControlNet caching and parallelization, Katz deploys ControlNet as a services, which enable ControlNet sharing, where a single ControlNet can be multiplexed by multiple base models. And second, Katz proposes a bounded asynchronous loading design, which has a LoRa loading overhead. So due to the large quantity of LoRAs in production, LoRa is usually fetched from a distributed LoRa storage system, which can incur significant loading overhead. And besides, caching popular LoRAs is ineffective in reducing loading overhead. So from the production trace, we observe that LoRa invocation has a long tail distribution. So the caching size to reduce the LoRa loading overhead is very large. To address this challenge, we analyze the text-to-image generation process and found that LoRa computations take effect largely in the later stages of the denoising process. So the figure on the left image shows the image generation process every 10 steps from the first step using a LoRa. And the top row presents the image generation process without using any LoRa. And the middle row presents the generation process with LoRa in the entire process. And the bottom row, we present the generation without using LoRa during the initial stage and with LoRa during the remaining stage. So in image generation, the initial denoising steps constitute a semantic parsing stage, wherein the model determines the image composition and layout. However, LoRa largely determines the details and the styles of the image generation, so we can safely exclude it in the initial denoising stage. And driven by this observation, Katz overlap LoRa loading with base model execution in the initial semantic parsing stage. So when a request arrives, Katz asynchronously loads the requested LoRa, and in the meantime, it starts a base diffusion model inference early to perform image generation without LoRa. And later, when the LoRa is ready, Katz patches it on the base diffusion model. And to ensure there is no quality loss, Katz imposes an asynchrony bound key for overlapping LoRa loading with base model inference, which means that if the LoRa is not ready before the bound key, the base model will not continue to denoise until the LoRa is loaded. And Katz also exploit parallelization opportunities to accelerate both base model execution with multiple GPUs. This is specially designed for the CFG operation in the denoising process, which is the dominant computation in the image generation. So while enabling CFG, the input latent tensor is duplicated and the two tensors are denoised, one conditioned on the text and another not conditioned. So as the conditioned and the unconditioned denoising have no data dependency, Katz can parallel them on different GPUs. And besides, Katz also includes several kernel-level optimizations to accelerate the base diffusion model inference. And putting it together, we present the architecture of Katz, a serving system specially designed for the diffusion workflow serving. And next, we show the performance of Katz. So here is the setup of our evaluation, and we consider 3 baselines. They are diffusers, Nirvana, and the distribution. And we evaluate Katz in terms of serving latency and the image quality using the commonly used image quality metrics. So here is the results of in terms of serving latency. We measure the serving latency of generating an image with different adapter settings. So in the left figure, we can see that compared to the baselines, Katz can achieve up to 7.8 times speed up. And in the right figure, we show the latency breakdown, where we can see that Katz can effectively eliminate the loading and computation overhead of the adapters. And next, we evaluate each baseline in terms of the image quality, as our bounded asynchronous adapter LoRA loading design slightly changed the image generation process. So as shown in the table, Katz can generate images with a quality compared to those generated by diffusers in terms of the quantitative metrics. And we also conduct a qualitative measurement that involves 75 human participants. According to the results, Katz rivals the diffusers and significantly outperform the Verna. And let me do a quick summary. So we present the first comprehensive calculation study of text-to-image serving workflows. And to mitigate the overhead result from adapters, we propose 3 key designs, namely ControlNet-as-a-Service, bounded asynchronous LoRA loading, and optimize the base model execution. And thanks for your attention, and I'm happy to take any question you may have.